Hi everyone, welcome back. In this video we're going to discuss right ascension, how it's helpful, how you can use it to calculate rising and setting and best viewing times of stars, planets, etc. So if you'll recall, there are two general celestial coordinates that are used to map stars and planets and other objects in the night sky that actually track the objects, at least ones that amateur astronomers often use, and those are right ascension and declination. And remember that declination is just like latitude. A line of declination in the sky is directly over that line of latitude on Earth projected onto the celestial sphere. Right ascension is kind of like longitude, but it's not exactly like longitude. It's kind of like longitude in the sense that an object of a certain right ascension, if you were to map that right ascension great circle over the celestial sphere, that would fall over a line of longitude on Earth. However, as Earth rotates, it would not always fall over the same line of longitude, because the whole point of the celestial coordinates is that as Earth rotates, we want the stars and other objects in the night sky to maintain generally the same coordinates, so that given those coordinates we can figure out where we need to point our telescopes and when to expect the objects, etc. So here's how the system works. Our sun is located at a right ascension of 0 hours. That's just the system. The sun's located at a right ascension of 0 hours during the vernal equinox. And as Earth revolves around the sun, that means that our sun's location relative to the background stars is going to change. In fact, the path that our sun takes during that time is called the ecliptic, and the constellations through which the ecliptic travels are called the zodiac. We'll have more to say about that in the next video. But in any case, what that means is that over the course of a year, our sun must traverse the whole ecliptic circle and then come back to that point where it's crossing the celestial equator. The vernal equinox is defined as the point where our sun crosses the celestial equator from south to north. We'll have more to say about that in a future video. But in any case, the spot that we call a right ascension of 0 hours is the location where our sun the location on the celestial sphere where our sun appears to cross the celestial equator from south to north. So its declination, of course, during that time is also going to be 0 degrees because it's crossing the celestial equator. The celestial equator is the declination line of 0 degrees because it's directly above Earth's equator. However, since our sun has to go through the whole circle in 12 months, that means that each month it goes through 1/12 of the circle. So the units for right ascension are hours, minutes, and seconds. So that means there are going to be 24 hours in the whole circle. So every month our sun increases its right ascension by 2 hours until it ends up coming back to where it started on March 21st. So what that means is that on April 21st our sun's right ascension is 2 hours, on May 21st it's 4 hours, on June 21st it's going to be 6 hours. That's the summer solstice. And I'll ask you a quick question. What is our sun's declination at the time of the summer solstice? Give you a minute to pause the video and think about it. So the answer, if you've paused the video and thought about it just to check your work or your thoughts, the answer on our sun's declination at that time is 23.5 degrees. To be more precise, 23.45 degrees. Why? Because that is the tilt of Earth's axis. On the summer solstice, our Earth is oriented such that the northern hemisphere, as much as possible, is tilted toward the sun. What is the as much as possible? Well, it's the tilt of Earth's axis, 23.5 degrees, or 23.45 degrees. So that makes our sun's declination at that time 23.45 degrees. Now, how is this helpful? So one way that you can think about this is if you have a star that is within 10 or 20 degrees of 0 declination, then you can figure out approximately that star's rising and setting time by knowing what our sun's right ascension is at that particular point of year. Because the whole point about right ascension is that if two stars having the same declination differ in right ascension by n hours, then that means the object with the so-called later right ascension will be in the same place as the object with the so-called earlier right ascension at a time n hours later than the earlier object. So that's how you can use that. So if you have two stars that are at the same declination, one of them has a right ascension of 4 hours and the other one has a right ascension of 6 hours, and you see the star whose right ascension is 4 hours directly south 20 degrees above the horizon, well, the star with a right ascension of 6 hours will be directly south 20 degrees above the horizon 2 hours later. That is 6 hours being 2 hours later than 4 hours. So this only works relatively well if you're either comparing stars that have the same declinations, or if you are comparing stars with our sun, whose right ascension you can figure out. Now keep in mind that the farther you go away from the celestial equator, the larger your estimates will be off, unless you're comparing with another star whose times you know separately for some reason. So our sun has a right ascension of 6 hours, declination 23.5 degrees during the summer solstice. Well, that means that stars with a right ascension of 18 hours will be at their best visibility on that day at midnight, because that is, they have a right ascension that's 12 hours different from the sun, so they're going to be rising when our sun is setting because their right ascension is 12 hours different, which means exactly halfway across the sky, so that by midnight those stars are going to be due south, which is in many cases going to be when their best visibility is going to be. So that can often be useful for figuring out what time of year is going to be the best time to view a star. So in terms of using right ascension, so let's consider October 21st, when our sun has a right ascension of 14 hours, because you know that on the autumnal equinox, that's halfway through the 12-month cycle, so our sun is going to be halfway through the right ascension cycle. Well, it started at 0 on March 21st. Halfway through the 24 hours is 12 hours. So our sun's right ascension on September 21st is going to be 12 hours. And since it increases by 2 hours per month, that means that on October 21st, it's going to be 14 hours. Okay, well, consider the star Sirius. Sirius has a right ascension of about 6 3/4 hours. Its declination is minus 16 degrees, which we will consider to be approximately close to the celestial equator, though how approximate that is depends on who you ask. But our sun, well, we'll just pretend that our sun rises at 7 a.m. on October 21st. In truth, it's going to rise later than that because our sun's declination is going to be less than 0 at that time. So when something has a declination less than 0, it will rise later than you think, and it will set earlier than you think. So Sirius, on October 21st, Sirius always has a right ascension of about 6 3/4 hours, but on October 21st, our sun has a right ascension of 14 hours. We just mentioned that in the last slide. So Sirius's right ascension, well, what is 14 hours minus 6 3/4 hours? That's going to be 7 1/4 hours. So Sirius's right ascension is 7 1/4 hours before that of the sun. What does that mean? It means that Sirius is going to do everything 7 1/4 hours before the sun on October 21st. So if the sun rises at 7 a.m., then Sirius is going to rise at about 11:45 p.m. If our sun sets at 7 p.m., then Sirius will have set at about 11:45 a.m. So, in other words, that's why Sirius is not a star that you look for early in the evening during the autumn, because it's going to be below the horizon. But it will rise at about 11:45 p.m. Now, in truth, it will rise a little bit after that, because remember, its declination in this case is negative. It would only rise right at 11:45 p.m. if its declination was 0, that is, on the celestial equator. So you have to make some allowances for that if you're using this method to estimate when something's going to rise and set. In the case of Sirius, it's going to rise after you think it should. It's going to set before you think it should, because its right ascension, or sorry, the declination circle on which it is on, most of that circle is below our horizon in the northern hemisphere. So, let's consider a full example. At approximately what time of year does the star Sodom-Malik in Aquarius rise at sunset? That is, at what time of year will it probably have its best visibility, because you'll be able to see it at midnight. So Sodom-Malik's right ascension is 22 hours and 5 minutes. We'll just round that to 22 hours. And we're going to, since Aquarius is a zodiac constellation, we'll assume that it's reasonably close to the celestial equator. That is declination 0. So we'll assume that we can actually apply this method to Sodom-Malik, assuming that I'm pronouncing the star correctly. I hope I am. So we write down our givens, right ascension, which we're going to round to 22 hours. Well, There are two ways we can think of this. First, I'll show you what I have here, and then I'll talk you through it. First, you consider the fact that on March 21st, it would rise 22 hours after sunrise. That is, at 4 a.m. But we want to see it at 6 p.m. Well, 6 p.m. is 10 hours earlier than 4 a.m. So what does that mean? It means that, well, each month after the vernal equinox subtracts 2 hours off of the rising time, because our sun's right ascension increases by 2 hours per month. So that means the rising time of stars, background stars, is going to decrease by 2 hours each month. So we want to wait until 5 months later so that it rises 10 hours earlier than 4 a.m. Because after all, we want it to rise at 6 p.m., that is sunset. And this is assuming no daylight saving time, by the way. So we might have to correct that, if it turns out that we realize that we're going to be in a daylight saving time area. So March 21st plus 5 months turns out to be August 21st. So first of all, the answer is not exactly correct because we rounded the coordinates. Second of all, we do need to take daylight saving time into account. But here's the thing. Do we really need to take daylight saving time into account? Because after all, we want this to rise at sunset. So it's like, okay, you're taking into account daylight saving time, but here's the thing. Sunset is sunset. So it's like, yeah, you have to add an hour for daylight saving time, but you would also have to subtract that off by realizing that we have to take that into consideration with the star as well. So either way, it's going to rise at sunset on August 21st. Here's another way of thinking about this. So its right ascension is about 22 hours. So what that means is like, okay, we want it to rise at a time, it's going to rise at sunset at a time of year when its right ascension is 12 hours different from that of our sun, so that it's on the opposite part of the sky. Well, what time of year is that? Well, that's going to be at a time of year when our sun has a right ascension of 10 hours. 22 minus 12. Advanced math there. So, when's our sun's right ascension 10 hours? Well, it goes through 2 hours per month, so that's going to be 5 months after when its right ascension was 0. Well, its right ascension was 0 on March 21st, so we wait until August 21st. That is 5 months later, so that our sun will have a right ascension of 10 hours then. And thinking about it that way, we didn't even need to let the idea of daylight saving time enter our minds. Okay, so again, this only works when you're relatively close to the celestial equator. If the declination is farther north, then it's going to rise earlier and set later than you think. And that's, if you're in the northern hemisphere, well, our sun has a positive declination between March 21st and September 21st, so it rises earlier and sets later than you would think, and hence it's up longer. We're going to have a lot more to say about that when we discuss the seasons in a couple more videos. Here's another example. Consider the star Mintaka, which actually is literally right on the celestial equator. It differs from the celestial equator by less than a degree. So, what time will Mintaka rise on September 21st? So, it has a right ascension of about 5.5 hours. So, let's see now, 5.5 hours, that's, we'll say 5.5 hours. Well, our sun has a right ascension of 0 on March 21st. So, 6 months later, on September 21st, our sun has a right ascension of 12 hours. So, Mintaka's right ascension of 5.5 hours, well, that is 7.5 hours before, 6.5 hours before the right ascension of our sun. So, taking daylight saving time into account here, because we are asked about a time, our sun rises at 7 a.m. on September 21st. Again, taking daylight saving time into account, it rises at 7 a.m. So 6.5 hours before 7 a.m. would be 12:30 a.m. on September 21st is when the star would rise. Again, taking daylight saving time into account. Now, if you live in a state like Arizona, or I think Montana doesn't do daylight saving time, or a whole lot of the rest of the world doesn't do it, then the answer would just be 11:30 p.m. which is what we calculated here. But yeah, taking daylight saving time into account, if you're in the Eastern time zone like we are, and all of the states in the Eastern time zone do daylight saving time, then it would rise at 12:30 a.m. on September 21st. Okay, so that's all we're going to have to say about right ascension for now. In the next video, we're going to examine constellations, the origins of constellations, and how the zodiac came about. So until then, I'll see you, and thank you all for watching.